you, and thanks for the invitation. So the setting of what I'm going to be talking about is exactly the one that Sergio was talking about a couple of days ago. So we have M, a closed hyperbolic three-manifold, and we'll talk about different classes of flows on such a manifold. So the first kind is a pseudo-anossive flow. So this, as Sergio mentioned, is a flow that's defined by sort of a coarse, that's defined by some sort of transverse hyperbolicity, that there's some transverse structure that kind of captures the fact that orbits are kind of converging in some directions and they're diverging in others. So there are two foliations, two-dimensional foliations, the stable foliation and the unstable foliation. And the picture is that if you have any flow line, there's, let's say, draw in red, a stable leaf that goes through this, and any other flow line that's in this other stable leaf is asymptotic in the forward direction to this guy. And in the other direction, there's a sort of unstable leaf. And here, flow lines are converging in the backwards direction. This is the picture for an anossive flow. And pseudo-anossive means that we allow certain kinds of singularities, these p-prong singularities, which are not too important. For the moment, you can just think of it in terms of some examples. So the easiest example is the case of a suspension flow. So you take some closed, or let's say closed hyperbolic surface, and we'll take the surface cross I, and we take some pseudo-anossive homeomorphism of the surface. So that means that you have a pair on the surface of perhaps singular foliations, one of which is contracted and the other one is expanded. So if I put a flow on this three-manifold that just kind of goes in the vertical direction, when I glue it up, I'll get a flow on the glued-up manifold, and the stable and unstable two-dimensional leaves are just what I get by flowing the one-dimensional stable and unstable leaves around this picture. So this isn't the canonical example. Really, this sort of started by studying the geodesic flow on a closed hyperbolic surface. And as Sergio mentioned, this picture of that suspension flows are pseudo-anossive kind of generalizes to the case of taut finite depth foliation. So this is a taut depth zero foliation by surfaces. And in general, if you have a taut finite depth foliation, there's some flow transverse or almost transverse to that foliation that's pseudo-anossive. So, I mean, there are various reasons for which these flows are important. I mean, intuitively, I don't know, someone once explained to me that this kind of stretching and contracting behavior is kind of generic for things that get mixed up. So, you know, imagine just pouring some milk into your coffee and stirring it. You kind of see the directions where it stretches and contracts. And for anossive or pseudo-anossive homeomorphisms of surfaces, this is an actual rigorous thing, meaning you can generically, things that get mixed up kind of can be perturbed to have an anossive structure. But for the kind of low-dimensional geometers, I can give you a little more propaganda. One of the places you can use these flows is to understand faces of the Thurston normal. So we'll look at the two-dimensional homology of our manifold with real coefficients. And Thurston defined this norm. So if I take a class here, the norm of it is just, well, I look at all embedded surfaces that represent this cohomology class, and I look at minus the Euler characteristic, or chi minus, which is really the Euler characteristic where we forget any sphere components. And we look at the infimum of this over all surfaces that represent this homology class. So Thurston showed that the unit ball of this norm is some rational polyhedron, so it's a polyhedron with rational vertices, and the faces of this sort of polyhedron organize either fibered classes or non-fibered classes, in the sense that a face here, which we'll call maybe a fibered face. So a face is called fibered if some integral homology class in the cone over this face is represented by a surface that can be made into a fiber. And if one of those represents a fiber, then every integral class in here represents a fiber. So the use of pseudo and also flows here is, well, this general fact that corresponding to this fibered cone, C of F, there's a flow phi that's pseudo and also on the manifold. And now if I take any integral class here in the interior of this fibered cone, I can represent it by a surface that's transverse to this flow. And in fact, the fact that this is transverse to the flow actually tells you that this is a norm minimizing surface. So it certifies that this surface has minus Euler characteristic exactly the norm of this class. Now there are a few. So you can generalize this in some sense to non-fibered faces. So this is a result of Fried's. And the general idea of this is that you can see, well, you can look at, say, the sort of the geometric, or well, the algebraic intersection of this surface with any closed orbit of the flow. And this has positive algebraic intersection number. And this implies, I'll put this in quotes, that the algebraic intersection number of the surface with any orbit is positive. So this doesn't really make any sense to write, because this is, I'm not talking about closed orbits here. But the idea is just, you want to make sure that the other flows of your flow kind of pass through some representative of the surface positively, and you can show that you can then perturb the surface to make it actually transverse to the flow. Now, the reason this sort of thing works, so this is, I did mention Fried, the reason this sort of thing works comes down to something called the Inosov closing lemma. Which tells you that you can kind of approximate recurrent orbits by actual closed orbits. So the full statement is, if I take kind of let's say what I'll call an almost cycle. So a long orbit, or a long segment of an orbit, whose endpoints are close together, that's an almost cycle. Then there's an actual closed orbit nearby. So that's what it means if I just check that the closed orbits kind of pass through the surface positively, then all the orbits, more or less, positively. Now the idea behind this really just uses this transverse contracting expanding structure. So a little cartoon of the proof. Well, the endpoints of this sort of long almost cycle are nearby. So that means that if I draw the two unstable leaves, kind of local unstable leaves through the beginning and the end of this almost cycle, then the unstable leaf through here will intersect the stable leaf through here, and vice versa. So let's say red is stable and blue is unstable, even though, just because I'm used to that, even though it tends to annoy my collaborators. So these are really it's this cross, some small interval. You might think that these are the strong stable leaves, but they're not. They're just kind of close to strong stable leaves. This is just a picture. Oh, okay, then don't worry about it. So this is maybe you've taken some transverse disk and you've intersected the stable and unstable leaves with that, and that's what these lines are that I've drawn. So now what happens if I take this point here? Actually, I need to take this point here, and I flow it forward. Well, about halfway along this almost cycle, the picture looks kind of like this. And now I've started along the stable leaf through this point. So as I flow forward, this yellow orbit is going to get closer to this white orbit. So at the end, I'll end up somewhere here. And it'll be closer to this. This will be closer to this than this is to this. Now, if I flow this backwards, well, with respect to this guy, it's on the unstable leaf. So as I flow backwards, it's going to get closer. And I'll get something maybe over here. And now it's closer. So now I can do the exact same thing. I have the same kind of picture, except the distances are even smaller. So as I bounce, I can just kind of do this over and over again and bounce back and forth, and I get a sequence of these almost cycles of comparable length, but now their endpoints are getting closer and closer together. And in the limit, I'll get an actual closed orbit. Okay, so another kind of important part of the picture for pseudo and also flows is this universal circle that Sergio mentioned. And we'll come back to this, but for now I'll just say that if I take any pseudo and also flow, there's a way of constructing an action of the fundamental group of the manifold on what's called a universal circle. So this is just a topological circle, and this action is a faithful action by orientation preserving homeomorphisms. So this already tells you something, because not all three manifolds fundamental groups admit circle actions, as you heard in Dave's talk at the beginning of the conference. So for example, this tells you that the Weeks manifold has no pseudo and also flows. Okay, so the other class of flows that we're interested in are the quasi-geodesic flows. And at first, this sounds very different. So quasi-geodesic just means that the flow lines, when I lift to the universal cover, are quasi-geodesic. In other words, distances measured along flow lines are kind of coarsely comparable to distances between points. More specifically, so here's some curve in some metric space. If I take 2 points on this curve, I can measure the distance sort of directly in the metric, or I can measure the distance along this flow line. And saying that this curve is a k epsilon quasi-geodesic means that we have the following kind of bound. So the distance along the curve between the points x and y is bounded by a multiple of the distance, the straight line distance between these points, plus some wiggle room. Now, in hyperbolic space, quasi-geodesics have some very nice properties. So I'll draw the picture in H3. First of all, any quasi-geodesic will have 2 well-defined endpoints on the boundary of hyperbolic space, and these endpoints will be distinct. Moreover, if I connect the 2 endpoints of this quasi-geodesic with the geodesic, then the quasi-geodesic kind of fellow travels this geodesic. Specifically, it stays within some kind of bounded neighborhood of this geodesic, where the bound depends only on the quasi-geodesic constants. So again, a flow on a hyperbolic 3 manifold is quasi-geodesic, just if every flow line lifts to a quasi-geodesic in the universal cover. So the main examples of these flows are, well, I already have them here, suspension flows. So these suspension flows are both pseudo-analysive and quasi-geodesic. And actually, not just suspension flows, but this manifold is fibered by surfaces, and any first to the fibration by surfaces will be quasi-geodesic by the argument that Sergio explained. So you look at the cyclic cover corresponding to this, and there's sort of a maximum amount of time it takes to get between two different copies of the surface, and there's also a minimum distance between the two surfaces. So if you follow a curve for long enough, it'll eventually make some progress in the manifold, and that's really all you need to show that your flow is quasi-geodesic. And again, the pseudo-anosa flows transverse or almost transverse to top finite depth foliations are also quasi-geodesic. So the main, okay, well, there's also another parallel here. So you can also say that quasi-geodesic flows represent faces of the Thurston norm ball, just because, well, actually the flows here that I'm choosing to represent these faces are also quasi-geodesic. But it gives you a little extra power because, I told you that if you have an integral class in the interior of this cone, it can be represented by a transverse surface. But if I take an integral class maybe on the boundary of the cone, that's not necessarily true, but you can homotop the flow. You can do some little blow up of the flow to make any surface on the boundary of this transverse, and that blow up can be done in a way that preserves quasi-geodesicity. So it can be useful to think of quasi-geodesic flows rather than pseudo-anosa flows representing fibered faces. And in fact, also there's one kind of fully general statement I can make, and that's a theorem of Danny Caligari's. So one way to compute in quotes, the Thurston norm ball is to look at, so you look at the set of all Euler classes of quasi-geodesic flows. So these things live in not H lower 2, but H upper 2. And you take the hull of these. This hull is exactly the Thurston norm ball. Or, well, actually, the dual Thurston norm ball in H upper 2. All right. So, okay, the main theorem I want to tell you about today is, so I mentioned for pseudo-anosa flows, you have it's kind of easy to find closed orbits, and Caligari conjectured that the same should be true for quasi-geodesic flows. Yeah. Yeah, for each vertex, you can, you can find a quasi-geodesic flow. I mean, I think you can do that for pseudo-anosa flow also. But maybe this exact equal statement doesn't work. Or, well, it probably does work, and there's some work of Mosher that kind of extends this picture, for fibered faces to non-fibered faces in some special cases, and you need some extra restrictions. So it would be interesting to know sort of a fully general picture. So, given a face in general, can you find a quasi-geodesic flow or a pseudo-anosa flow that represents that face in the sense that any homology class in that face is represented by a surface transverse to that flow? And so for many cases, it's true if the flow is something, there's a condition set called no dynamically parallel orbits, whatever that means. Yeah, I mean, this picture, I mean, so I didn't exactly tell you what you can use this kind of picture for, but there are a lot of questions. So one thing you can do, I mean, so in this fibered face, each integral class represents a fibration. And corresponding to that, you have a dilatation, meaning it's a fibration. The monodromy of that fibration is a pseudo-anosa map. And you can ask what the dilatation is. And it's known that if you go off to the boundary of a fibered face, the dilatation blows up. So you should be able to see this fact geometrically by understanding how how the representatives sit with respect to the flow, because the dilatation, meaning the pseudo-annulsive map, is exactly the time one return map. Sorry, the first return map of the flow. So you should be able to, by seeing how these surfaces lie with respect to the flow, you should be able to read off, maybe not exactly the dilatation, but see that it blows up. Okay, so the main theorem I want to tell you about is this conjecture of Caligari's that quasi-geodesic flows have closed orbits. And in fact, they have many closed orbits. And the way we'll show this is by proving some sort of some analog of the annulsive closing lemma that maybe we'll call a homotopy closing. And we'll have something like this. So I'll explain exactly what this means a little later, but the main ingredients of this are, first of all, pseudo-annulsive flows. I guess I've erased them. Pseudo-annulsive flows are kind of defined by some sort of transverse contraction expansion condition, whereas quasi-geodesic flows are defined by some tangent condition. But there's this surprising fact that when the ambient manifold is hyperbolic, there's some sort of coarse contraction expansion. And for the moment, this doesn't make sense because what exactly is being contracted and expanded? In the case of a pseudo-annulsive flow, we have these foliations that are sort of contracted, expanded. We'll get to that. There's some sort of generalization of a foliation where this works. But for the moment, if you just imagine that you have actually foliations and they're coarsely contracted, expanded. So what I mean is if I start at 2 points that are far apart, if I flow for some time, they'll get closer and they'll eventually end up within some finite distance of each other, but they may not contract fully. So it's pretty clear that the argument that I mentioned for the annulsive closing won't work for this, because there you need actual, on the nose contraction expansion of these foliations. So the second part of this will be to use a universal circle. So again, for quasi-geodesic flows, we have some action of the fundamental group of the manifold on a topological circle. And this circle, I want to argue, captures a lot of the large-scale dynamics of the flow. So if we state this coarse contraction expansion in the right context and use this group action that captures the large-scale dynamics, we can get some sort of closing lemma. Now there's a bigger picture to this, which is, so I'm trying to tell you that quasi-geodesic flows are kind of coarsely like pseudo-annulsive flows. And in fact, it should be stronger than this. So there's another conjecture by Caligari that any quasi-geodesic flow can be deformed to a flow that's both quasi-geodesic and pseudo-annulsive. In fact, it can be deformed through quasi-geodesic flows. And I think that this I'd say is most likely almost entirely true. And I chose those words very carefully, and I'll try to give some indication of why this is. All right, so I think that's enough propaganda. Let me get to the actual picture. It's the big board. So again, we have some closed hyperbolic three-manifold, and we have some quasi-geodesic flow. Now, the universal cover of this manifold is hyperbolic three-space. which I'll draw in the unit ball model. And I can lift this flow to a flow upstairs. Now, as I mentioned, the flow lines of this flow will have well-defined endpoints in the boundary of hyperbolic space. And moreover, the endpoints of nearby flow lines vary continuously. So what we'll do is look at the flow space, which is just the orbit space of this lifted flow. So I'll call this P, and this, so this is, as a set, this is the set of all lifted orbits, and the topology I use on this is the quotient topology. So I just take H3 and I collapse each flow line to a point. And so this is kind of a locally two-dimensional space because I can locally find kind of little transverse surfaces to this flow. And in fact, it's Hausdorff. So that's something proved by Caligari, which means that, well, it's the plane. So I'll draw it as kind of an open disk. Now, a point, we'll call it P in this flow space, corresponds to some flow line, some lifted flow line, which maybe I'll write as P cross R. And now I can think of two different maps, E plus and E minus, that take this point to the corresponding positive and negative endpoints of this flow line. So this is E plus of P, and this is E minus of P. And really, well, this map is going to the boundary of hyperbolic space. Now, the fundamental group acts on H3 by deck transformations, and it preserves the foliation by flow lines, so it descends to an action on this plane. So you can probably already guess where this universal circle is going to come from. I'll find some way of compactifying this plane to a closed disk in such a way that I can extend the pi1 action. And that'll be my universal circle. So how to do this? Well, what we can do is take sort of any point on the boundary of hyperbolic space, we'll call it Z, and I'll look at all of the flow lines, all of the lifted flow lines that limit to this point in the forward direction. I can think of this, if I like, as a subspace of P, and that subspace is just, well, it's under the positive endpoint map. I'm taking the preimage of this point Z. So that draws out kind of some subset of this plane, maybe disconnected, maybe kind of complicated, but for reasons I'll explain in a moment, each component of this will be some unbounded set in the plane. So I'll call each component of this preimage a positive leaf. So if I vary the points on the boundary of hyperbolic space, I'll kind of fill up this whole plane by a bunch of closed unbounded sets. And I'll stick these all together into something I'll call D plus, or the positive decomposition. So again, this is just a set of components of E plus inverse of Z, where I look at all points in the two-spheroid infinity, the boundary of hyperbolic space. So similarly, I can do the same thing using the E minus map. And I'll get kind of another decomposition of this plane that looks like this. And I'm drawing this suggestively to look like these things are kind of intersecting transversely, although that's not exactly true. But what is true is that so first of all, each leaf is unbounded. And moreover, if I take a positive leaf and I intersect it with a negative leaf, I'll get a compact set. So this second property is easy to see, because what is this really? If I take a particular positive and negative leaf, well, that means that's a subset of all the flow lines that go between two particular points on the boundary of hyperbolic space. And remember that these all live in some bounded neighborhood of the geodesic between these 2 points. So in particular, they all intersect some compact set here. which projects to a compact set in the plane. The more complicated assertion is that each leaf is unbounded. And this is really one of the very basic facts for quasi-geodesic flows, and it's the fact that gives it all of the structure we need. So I'll just kind of sketch this idea. Well, so let's say we had, so this is, I'll draw here the pre-image of some point under the E plus map, and let's say one of my leaves is bounded. So I can separate it from all of the other pieces of this pre-image by some compact disk. And if I like, I can think of this disk as being a transversal to the flow in H3. So in fact, you can, we have this projection map from H3 to this plane. You can always find a section of this. So if I like, I can think of this plane as a transversal to the flow. And that uses, some results of, I think, Montgomery and Zippin from the 1920s. So it's from whatever came before the prehistoric era, I guess. Okay, so what's that? So okay, so here's the lift of my disk, and what I imagine is the flow lines, the positive parts of the flow lines that come off of the boundary of this disk. And this draws out some set in the boundary of hyperbolic space. Meaning this is really, this set over here is the image of this thing under the E plus map. Now, the fact that I have this thing in here means that there's some flow line that has a different endpoint here, which means that this set here is separating. So it has some interior. Well, actually, the set of all negative endpoints of flow lines, I can write that as just E minus of P, as a subset of the boundary of hyperbolic space has to be dense, just because it's invariant under the deck action. So that means that there's some point here that's the negative endpoint of a flow line. So there's some flow line kind of going in this direction, but that can't be. Where's it going to go? It would have to crash through this disk in the wrong way. So that's how you see that each leaf is unbounded. So I mean, this means that this, even though you can think of this plane as a transversal to the flow, it's not embedded in a very nice way. It's kind of really badly twisted up. So now the idea is to use these two decompositions, these positive and negative decompositions, as if they were singular foliations of the plane. So if you imagine instead of a quasi-geodesic flow, you had a quasi-geodesic pseudo-and-also flow, or just a pseudo-and-also flow, well, you'd have two-dimensional foliations, the stable and unstable foliations. Those would lift to two-dimensional stable, unstable foliations here, and they'd project to stable, unstable foliations here. And as Sergio said, in the case of a pseudo-and-also flow, there's kind of a natural way to compactify this plane using special nested sequences going out to infinity. And there's a generalization of that we can use for this case. And in fact, there's kind of a nice way to give it kind of a universal property. The idea is, okay, let's say we just have a plane, and we have some unbounded subset of the plane. What does it mean to have an end of this unbounded subset? Well, I can start cutting out compact disks. I cut out this disk, and I choose some component of what's left here. And I'll call that, maybe I'll call this whole thing K, this whole unbounded set K, and I've chosen this subset K1. Now I cut out a larger compact disk, and now within this subset K1, I have two choices to make. And let's just say I choose this one. So this is contains K2, just this sort of piece over here. And then I keep doing this. I cut out larger and larger compact sets, and I get a nested sequence like this, K3, and so forth. And this is what I'll call an end. So this is Freudenthal's theory of ends, for those who recognize it. Now let's say I had a compactification of this plane. And there are many compactifications. But I can sort of see what this end will do in the compactification. So by compactification, I just mean an embedding of this plane in some compact set so that the image is dense. Well, maybe I'll use iota. So the impression of this end, well, I'll just define it as, well, the intersection of the closures of these ki's, where I take the closure in my compactification. So this intersection will give me some connected subset of my my compactification minus p. So the way to kind of universally build a compactification is to insist that it has some nice properties. So first of all, it makes sense to have each end of each sort of element of these two decompositions makes the impression of just a point. And maybe I also want the impressions of ends to be dense in what I get. And that, there's a kind of a universal space that characterizes that. And this works, this is not something special about quasi-geodesic flows. If I just have some kind of finite family of what I'll call unbounded decompositions of the plane, and I'll suppose that they intersect compactly. So each one of these is a decomposition of the plane. Each element of each one of these is closed and unbounded. And if I take elements from two different ones, their intersection is compact. So then there exists a unique compactification to a disk. So we'll call it p hat. And this will be just p together with some boundary circle that I'll add, such that first of all, the impression of each end of any one of the leaves of here is just a point. The set of all impressions of ends is dense in the circle I added. And third, it's universal with respect to these properties. So what I mean is if you have any compactification of the plane where impressions of ends are points and the set of all impressions of ends are dense, then actually it's just a quotient of some universal one. So that's it. That's how I get a natural boundary for this plane. So now I can stop drawing this as an open disk and draw it as a closed disk. And remember that the fundamental group acted on the plane, and it's easy to see that that action preserves the two decompositions. And what it'll do to the ends is it'll permute the ends in some nice cyclic way. So the action of the fundamental group on P extends to an action on the compactified flow space. And then just the restriction of this action to this circle is my universal circle. So this recovers what I mentioned before, Caligari's theorem that quasi-geodesic flows give you universal circles. And moreover, it shows that the universal circle can be thought of naturally as the boundary of the flow space. OK, so what's next? All right, so I mentioned before that this circle action somehow captures the large-scale dynamics of the flow. And, well, one thing it does is it recognizes closed orbits. But before I get to the full picture of that, there's kind of a cute little subcase I can think about. So what I want to claim is that by looking at elements of this action of fundamental group on the universal circle, in some cases I can spot closed orbits of the flow. So first of all, how can I recognize a closed orbit in terms of the action on the disk? Well, if I have some element of the fundamental group and it acts on this plane and it fixes some point x, then this exactly corresponds to a closed orbit in the free homotopy class represented by G. I mean, just because this means that this point here corresponds to some flow line, and there's a G that preserves this flow line, so it projects down to a closed orbit. So this might sound kind of silly, but it's useful in practice. So suppose some element of your fundamental group acts just on the universal circle with no fixed points, then there is a closed orbit in the free homotopy class represented by G. And the proof of this is just Brouwer's fixed point theorem. Because the circle is the boundary of the plane of the disk, so so it has to have a fixed point somewhere. The full picture, I mean, you can generalize this in a couple of ways. There are more ways to find closed orbits, but the full picture will require a little more work, and we'll have to bring in this sort of coarse contraction expansion, and we'll have to kind of state this coarse contraction expansion in terms of the action on this flow space or of this circle. But before we go there, there's some other kind of interesting aspects to the basic theory of quasi-geodesic flows. So remember that we have these endpoint maps that take points in the flow space to the positive and negative endpoints of the flow lines. In fact, these extend continuously to the compactified flow space. So these are continuous maps from p hat to s to infinity. And actually, these two maps agree on the boundary circle, so on the universal circle. So if I just look at a map that I'll just call E from the universal circle to the two-sphere at infinity, I have a fundamental group action here, and I have a fundamental group action here. And this map is pi1 equivariant. It's the image, I mean, so this is a circle, so its image is closed. It has to be dense because it's invariant under the action of the fundamental group of a hyperbolic three-manifold. So this is some pi1 equivariant sphere-filling curve in the boundary of hyperbolic space. So this kind of generalizes the famous Cannon-Thurston theorem. So Cannon-Thurston proved this sort of thing where they, effectively what they did was they did this for suspension flows. But this works now for any quasi-geodesic flow on any closed hyperbolic three-manifold. What else? All right, well, let's get to, we'll try to give you some idea of how you actually find closed orbits. So this coarse contraction expansion I've been talking about obviously is going to live on these sort of decompositions that I've built. And at some level, or I should say that Caligari built, and on some level this is easy to see. So if I take one of these leaves, and now I'll just think of it as a, yeah. Oh, okay, yeah. So the idea is that if I take a sequence of points that goes out to the boundary, the corresponding flow lines have to kind of go out. They have to escape compact sets in hyperbolic space, which means that the positive and negative endpoints have to get closer and closer together. Good question. All right, so if I just draw one of these, say, positive leaves, it's kind of obvious that there's some coarse contraction going on, right? Just because everything here is kind of limiting to a single point in the boundary of hyperbolic space. So things, even if I start far away, I'll eventually kind of get closer and closer together. But really the right way to think of this is in terms of the action of the fundamental group on the flow space. I think it's time to actually tell you what the homotopy closing lemma is. All right, so let's just take an orbit of the flow, and we'll take a forward recurrent one. So this is a flow on a compact manifold, so there have to be such recurrent orbits. Now, what I want to do is kind of represent the forward homotopy class of such an orbit. And the way I can do this is, well, I sort of keep winding around and getting closer and closer to myself. Well, I'll just take longer and longer segments of the flow, and I'll close them up by shorter and shorter little arcs. And I'll get, from that, a sequence of elements of the fundamental group, which I'll call an omega sequence. Now, there's one extra condition on the kinds of orbits I can look at. So I'll suppose that gamma has linked leaves. So what I mean by this is I can take my orbit in my manifold, I can lift it up to H3, and now it corresponds to just some point in this flow space, and I can look at the positive and the negative leaves through here, and the ends of these leaves make an impression somewhere on this universal circle, and I'll say that it's linked if it's linked, meaning if the ends of one separates the ends of the other. Well then, the GI eventually represent closed orbits. Meaning, at some point, all of these elements of the fundamental group will actually represent the free homotopy classes of closed orbits. Or, well, maybe a multiple, or some power of them will. So this is really except for this little extra condition that we need this orbit to be in the right kind of topological position. I mean, so it might look more complicated, but as long as I have something that looks like this. But this is sort of clearly a direct analog of the Ionosov closing lemma. So the rest of the closed orbits theorem just comes down to showing that there are closed orbits in this nice kind of topological configuration, and that's more or less just kind of topological arguments about decompositions of the plane. So I mean, to give you an idea, one simple thing. So in order to find kind of leaves that are linked, well, I at least need to know that there are some leaves that have more than one end. And that's something I can show kind of quickly. So D plus, say, contains a leaf with at least two ends. And the proof of this is kind of simple. Well, otherwise, if each one of these positive leaves has just one end, I can build a retraction from the disk to its boundary just by taking each point and sending it to the boundary point of its leaf. And there's a little, I've left out the detail. You have to know that this map is continuous, but you can trust me that it is. All right, so I just have a couple more minutes. And I guess I can say something about this bigger picture, how to say that a quasi-geodesic flow can be deformed into a pseudo-Ionosov flow. And the idea here is that this really, a lot of the structure of the flow, and even the structure of the manifold itself, is recorded in this universal circle. So, I mean, one thing to think about is, so for example, well, the general idea would be the starting point is take this plane together with these two decompositions and just make them into foliations in whatever way you can, or make them into singular foliations. So we can take this plane and we can take d plus and minus, and we can get something that we call the straightened flow space, and I'll have two singular foliations on this. And this you can kind of see how to do relatively easily. You just, if I start with a leaf, however complicated it looks, these things don't have to be locally connected. They're just closed unbounded sets in the plane. I'll just look at its ends, and I can sort of think of the family of all ends of leaves as defining a lamination on this circle. That's not exactly true, because I might sort of have more than one leaf sharing an end. So really, I have to kind of take the ends of all of these leaves that kind of meet up like this. And if I pretend that the interior of this disk is the hyperbolic plane, I can just take the convex hull of these guys. And for each negative decomposition, I'll also have sort of a convex hull, and I'll claim that they kind of intersect in the right way. So a four-ended guy here, a four-ended positive guy corresponds to a four-ended negative guy. So now I have a new pair of decompositions of this plane, and now all I'll do is anytime I see a positive hull intersecting a negative hull, I'll collapse that whole set down to a single point. And if you do this, so there's a theorem, I guess, due to Moore that tells you that the quotient will be a plane. So what we have now is we've just taken these decompositions and we've built a pair of singular foliations of a plane. And so what's the action on this plane? Well, it's kind of just determined by the action on the universal circle. And the action on the universal circle hasn't changed once I do this straightening and this decomposition. So at least on the level of the flow space, I've built an action of the fundamental group on a new plane together with a pair of singular foliations that looks kind of like it should be the action of a pseudo-analysis flow. So now the question is, how do I actually get a flow from this? And well, there are a couple of ways to do this, but one idea is to try to build it by hand. So remember that I can think of this P as a transversal to the flow. So that gives me a way of conjugating, so that gives me a way of looking at the flow on hyperbolic space as just a straight flow on P cross R. Meaning, right, I just take this embedding and I flow points either forwards or backwards. So this is, I know, homeomorphic to H3, meaning there is some natural identification here. So if I could take P cross R and I could just build an action on this, well, I know what the horizontal part of the action is. Actually, we're doing this in terms of PS. So I know what the action on this part should be. If I can decide sort of whether flow lines should shift up and down, meaning build an action on this whole thing in such a way that it's free and properly discontinuous, then the quotient is a three-manifold. And it's the same three-manifold by Mostow rigidity. So just finding any way of building this sort of action will give me, will kind of recover my entire three-manifold together, if I like, with the foliation by flow lines. And then I could try to just parameterize that to get a flow, and hopefully to get a Quasigeodesic, a pseudo-analysis flow. And that's, so this is a more general way to do it. There's actually kind of a more direct way to do this by, well, I can think of the flow on the left side as P cross R, and I can think of the flow on the right side as PS cross R. And I can, there is a way to kind of build a map from P to P, from P to PS, I should say, that kind of compares these things. And that'll let me kind of push the action on one side over to an action on the other side. So there are a bunch of details to check. Like, you have to check that this flow actually is pseudo-analysis. You have to show, contraction, expansion. one other detail that you need to check is that the flow you get at the end is still quasi-geodesic. Because what we're doing here is not some sort of small deformation. I'm just building an entirely new flow. And there's another interesting part of the picture that shows you that this universal circle the action on the universal circle remembers the action on the boundary of hyperbolic space. And well, I mean, on one level, it's pretty simple because, well, I have this, here's my universal circle, and I have this E map to S to infinity. So if I look at the decomposition of this by point preimages of this map, that gives me some decomposition of the circle, and I just collapse that down, and I can recover the boundary of hyperbolic space. But I can also do something a little sneakier, which is take two copies of the flow space. I'll call maybe P plus and P minus. And on P plus, now I'll build a map, we'll call it E twiddle, to boundary of hyperbolic space, where it agrees with E plus on the top, and it agrees with E minus on the bottom. So if I take a point preimage of this map, what I'll see is the corresponding kind of positive leaves on the upper hemisphere, the corresponding negative leaves on the lower hemisphere, and some of these maybe match up. And the point preimages are exactly what I get by gluing the decomposition up here to the decomposition down here in whatever way I need to keep it a decomposition. So now, in other words, there's a decomposition, maybe D twiddle here, and the fundamental group acts on this two-sphere, these two copies of the flow space, preserving this decomposition. And if I just collapse this decomposition, I recover hyperbolic space. So now I can use this to see that the resulting flow is quasi-geodesic, because this P cross R picture I can really think of as lying in here. Meaning the points cross R are really just lines connecting the upper corresponding points on the upper and lower hemispheres. So this means that flow lines have well-defined endpoints in the boundary of hyperbolic space, because they have well-defined endpoints in this sphere here, so they'll have well-defined endpoints in the quotient, and they'll vary continuously. And that, as Sergio mentioned, is enough to certify that your flow is quasi-geodesic. I think that's all I have to say.